imagine this. You're at your computer, right? And you need some really specific data. It's buried in this huge database. But here's the thing. You don't know any SQL, not a line. So instead of, trying to learn all that syntax or waiting ages for a data expert, you just type your question. Plain English, hit enter, and boom, the database just gets it. Gives you exactly what you need instantly. No complex code, no scratching your head over syntax, just the info you wanted.
Yeah, that really does sound almost like science fiction, doesn't it? But that's basically the promise of text-to-SQL, or as lots of people call it, natural language to SQL. NL2 SQL. It's this, groundbreaking tech that's moving incredibly fast. And the goal, to seriously lower the barrier for getting into relational databases, basically democratizing data science for everyone.
Exactly. And that's what this deep dive's all about. We really want to unpack how this, magic actually happens. We're going to look at how these AI models take our everyday questions and turn them into these really precise database queries. We'll also dig into the maybe surprising complexities, the real challenges these systems face, and, maybe the most interesting part, how researchers are getting better and better at building and evaluating these tools, properly evaluating them. We're drawing on some really recent cutting-edge research here, papers from places like the ACL Anthology, or AAK,
Right.
covering everything from prompt design, evaluation metrics, and, that tree multi-table querying stuff.
Right. So let's start with the basic idea, NL2 SQL. It's fundamentally about converting a natural language query, something like find the names of all customers who checked out books on exactly 3 different genres on Labor Day in 2023, and turning that into a SQL query that a database can actually run.
Okay, when you say it like that, it sounds maybe straightforward, like just translating, but I get the feeling it's not that simple.
Not at all. That's where it gets really, really interesting. Even for a human, like a database administrator, a DBA, this isn't trivial. It involves multiple, pretty complex steps. First, they have to really understand your intent. So breaking down that natural language sentence, identifying the key bits, names, customers, books, genres, Labor Day in 2023, and that specific constraint, exactly 3 different genres.
Got it. So just figuring out what I mean.
Exactly. And it's more than just keywords. Then there's what we call schema linking and content retrieval. This is where the DBA figures out which specific tables and columns in the database are actually relevant. Customers probably maps to a customer table. Genres might be literary genre or maybe subject genre. And crucially, this often needs real-world knowledge, domain knowledge, like your Labor Day in 2023 example for a U.S. database. That's September 4th, 2023. But if that database was, say, in China, Labor Day is May 1st, 2023, that context is absolutely vital.
Okay, that makes sense. So context is key. And then, after all that understanding, they actually have to write the SQL.
That's the final step, the SQL translation. And anyone who's worked with SQL knows there's often more than one way to write a query that gets the same result. You might use a natural join or maybe a subquery. Different valid approaches. It takes deep SQL knowledge to choose the best way or even just a correct way.
Right. So, okay, if it's already that complex for a skilled human DBA, what makes it even harder for an AI? What are those extra challenges?
That's a great question because the AI faces, inherent difficulties. Think about it. Natural language, it's fluid, it's flexible, full of nuance, sometimes messy. SQL, it's rigid, strict syntax. Like a formula, that difference alone creates a massive translation gap.
A mismatch, basically.
Totally. Plus, natural language is often ambiguous. One question could reasonably map to several different perfectly valid SQL queries. The AI has to figure out the intended one. And critically, NL2 SQL is super dependent on the database schema. If that schema changes, maybe a column name is updated or a table is restructured, the SQL needed for the exact same question will probably change too. The AI has to adapt constantly.
Wow, okay. That's a lot. So beyond those, like fundamental linguistic and structural hurdles, what about the practical side? The technical blockers engineers hit when actually building these systems.
Well, there are definitely practical hurdles, several layers. First off, efficiency, speed. These models need to return answers fast. You can't wait minutes for a query result. Latency matters.
Right. Users expect quick answers.
Exactly. Second, the SQL generated can't just be correct. It needs to be performant, optimized. An inefficient query, even if it technically works, could grind a whole database to a halt.
Not good.
Definitely not good. Third, cost is a big one. Especially with large language models, these things need serious hardware, and API calls can get expensive very quickly.
And I bet training data is a perennial problem, like with most AI.
A huge one. Finding high-quality training data for NL2 SQL is tough. It's scarce and often pretty noisy. Take the spider dataset, it's a standard benchmark.
Right.
Around 11,000 NL to SQL pairs. Just annotating that took something like 1,100 hours of human effort. And even then, it still had about 4% annotation errors that needed fixing later. It just shows the intense human labor involved. Then you've got privacy concerns. Sending potentially sensitive database info to external LLM APIs, that raises big questions.
Understandably.
And finally, trustworthiness. Users need to know the answers are consistently accurate, and ideally understand why the AI generated that specific query. Transparency matters.
Okay, so given all these massive challenges, how do researchers even start building these things? When we talk about LLMs powering text to SQL, what are the main ways they're used? What's inside the brain?
Broadly speaking, there are two main paths for using LLMs here. One is in-context learning. That's mostly about crafting really good prompts to guide the LLM without changing the model itself. The other path is pre-training and fine-tuning. That involves actually training or adapting the LLM specifically for the NL2 SQL task, making it a specialist. But regardless of the core model, you can think of a modern NL2 SQL solution as a pipeline, a series of stages.
A pipeline. Okay, I like that analogy. Walk us through it. What's stage one?
Stage one is pre-processing. This is all about getting the input ready for the main translation part. A really critical piece here is schema linking. That's connecting the words in your question customers' genres to the actual tables and columns in the database schema. Exactly. This can be done with simple string matching, sometimes more sophisticated neural networks, or even dynamic prompt modules using the LLM itself, like you see in systems like Denon-SQL or MagSQL.
So it's making sure the AI knows which parts of my question refer to which bits of the database structure.
Precisely. Then there's database content retrieval. This isn't just about the schema, but finding relevant values from within the database tables, like specific dates or names or product IDs that are mentioned or implied in the question. Methods here range from simple matching to more complex, efficient indexing, which is really important for big databases. And the last bit of pre-processing is often additional information acquisition. This is where the system might pull in extra context or domain knowledge to help the model understand better. It could be adding relevant examples or using external knowledge bases. For instance, the BirdR dataset, which is built for tougher evaluations, actually includes knowledge from like 95 different databases and 37 domains. That gives the model a richer context for complex real-world questions.
Okay, got it. So prep work done, input ready. Now we get to the core, right? The NL2 SQL translation itself. Where the magic happens, how does the model actually do the conversion?
Right, this is the heart of it. First is the encoding strategy. How do we represent the question and the database schema for the LLM? A common way is sequential encoding, just treating everything as a flat sequence of words or tokens. Simple, but you can lose some relational structure.
Like how tables connect.
Exactly, which is why graph-based encoding is getting really popular. It explicitly represents the database schema as a graph, tables, and columns as nodes, relationships as edges. This preserves that crucial relational structure, giving the LLM much richer context. Models like S2 SQL and Graphics-T5 use this approach.
Okay, that makes a lot of sense for databases, representing it like the structure it actually has. So once it's encoded like that, how does the model generate the SQL code itself?
That's the decoding strategy. The most basic is greedy search. At each step of writing the SQL, the model just picks the single word or token it thinks is most likely next. Many standard LLMs work this way.
Simple, but maybe not always optimal.
Can be. That's why there's beam search. It explores multiple possible sequences of tokens simultaneously. It's more resource intensive, but often finds better, more accurate SQL. But a really interesting technique is constraint-aware incremental decoding. Systems like Picard pioneered this. It builds the SQL query step by step incrementally. And here's the clever part. At every step, it checks that the generated part strictly follows SQL grammar rules. This drastically cuts down on producing SQL that's just syntactically wrong or incomplete.
Oh, that is clever. It's like building it with guardrails, ensuring it's valid as it goes. Are there other tricks used in this translation phase, like ways to guide the LM better?
Oh, absolutely. Task-specific prompt strategies are huge, especially with general-purpose LLMs. This means designing very specific prompts really carefully crafted to guide the LLM, often using techniques like chain-of-thought prompting to make the model think step by step, or decomposition, breaking complex questions down first. Models like Denon-SQL and MagSQL do this.
Giving it a better recipe to follow.
Kind of, yeah. Also, some systems use an intermediate representation. Think of it as a simplified halfway language, something between natural language and full complex SQL. maybe a SQL-like sketch. This can sometimes make the generation task easier for the LLM. NatSQL is a well-known example of this kind of intermediate language.
Okay, so the model has gone through all that. It's encoded the input, used a smart decoding strategy, maybe an intermediate language, and it's generated in SQL query. Is that it? Pipeline finished? Or is there a final buff and polish stage?
There definitely is. That's post-processing. It's all about refining that generated SQL. One part is SQL correction, trying to automatically fix any lingering syntax errors or maybe missing keywords. Some advanced models like DynSQL or MultiSQL's refiner agent actually have built-in self-correction capabilities.
The AI corrects itself. Cool.
Yeah. Then there's output consistency. This is interesting. The model might generate multiple candidate SQL queries for the same question. Then it executes all of them, and it uses a kind of voting system based on the results. If several queries produce the same result, that result is likely correct. It helps combat the randomness sometimes seen in LLMs. But it does increase the cost and time significantly because you're running multiple queries.
Right, like getting a second, third, and fourth opinion. Sounds robust, but expensive. What else in post-processing?
There are also execution-guided strategies. Here, the system actually runs the generated SQL and uses the results to potentially refine the query further. This is particularly useful for checking correctness against large databases. Systems like CodeS and MS-SQL employ this. And finally, you might have N-best re-rankers. These take the top few SQL queries generated by the model and reorder them based on some additional criteria, trying to push the absolute best one to the very top.
Okay, wow. That pipeline is incredibly sophisticated. Pre-processing, core translation with encoding and decoding, post-processing. So we've built these complex systems. But the next big question is, how do we know if they actually work? How do we measure performance accurately? You mentioned earlier that figuring out if two SQL queries are equivalent is hard. This sounds like a real metrics maze.
It really is a maze, and it's much harder than it sounds. Traditionally, people use two main metrics, but both have pretty serious flaws. The first one is execution accuracy, or EXE.
Okay, that sounds simple enough. Does the generated SQL give the same result as the correct SQL?
Exactly. That's the intuition. If you ask for customers in New York and the AI's query gives you the right list of New Yorkers, EXE says it's correct.
Seems reasonable. What's the catch?
The catch is false positive. EXE can be really misleading. You can have two SQL queries that are fundamentally different. Maybe one is missing a crucial join condition, for instance. But just by coincidence, on the current data in the database, they happen to produce the same result set. EXE would mark that flawed query as correct, but change the data slightly, and it would fail or give wrong answers. So it's like getting the right answer, but for the wrong reason. It doesn't guarantee the query logic is sound.
Ah, I see. That's a major blind spot.
Yeah.
Okay, what's the other traditional metric and its problems?
The other main one is exact set matching accuracy, or ESM. This tries to be more rigorous by comparing the components of the predicted SQL query directly against the components of the gold standard query. It looks at keywords, table names, columns, conditions, etc. It aims for more syntactic similarity.
Trying to see if the structure matches.
Right, but its big weakness is false negatives. SQL is flexible. You can often rate the exact same logical query in many different syntactic ways. They mean the same thing, retrieve the same data. But ESM, being focused on exact component matching, often fails to recognize this equivalence. It penalizes perfectly correct queries just because they're written differently.
So it's too strict, in a way. It misses the meaning because it's stuck on the exact words. What kind of things does ESM get wrong?
Yeah, precisely. ESM trips up on a lot of common SQL variations because it's not really comparing the underlying logic. For example, it often ignores crucial join conditions or doesn't check limit values correctly. These can totally change the result. It also struggles with important keywords like left join versus inner join or case statements. It doesn't handle aliases properly, sometimes treating local aliases as if they apply everywhere. It only checks for distinct inside aggregate functions, which isn't always right. It can't parse in clauses if they have a list of values. It's often too simple, maybe only allowing one subquery or one union or intersect. It gets confused by queries pulling columns from subqueries. Basically, it's looking for a very specific textual structure. And if the generated SQL deviates, even if it's semantically identical, ESM often marks it wrong.
Okay, so neither EXE nor ESM is really cutting it. One gives false positive, the other false negatives. They don't truly capture if the AI generated a correct query. What's the way out of this metrics maze? Is there a better approach?
Yes, thankfully. There's a much better metric that's gaining traction called enhanced tree matching, or ETM. ETM takes a fundamentally different approach. It doesn't just look at the text of the SQL. It first parses both the predicted SQL and the gold SQL into their abstract syntax trees, ASTs.
Abstract syntax trees, like a diagram of the query's structure and meaning.
Exactly. It represents the query's logical structure. Then, ETM applies a set of mathematically verifiable equivalence rules. These rules allow it to transform different-looking ASTs into a standardized or normalized form if they are semantically equivalent. Then it compares these normalized trees. This is key. It lets ETM see past superficial syntactic differences like different aliasing or slightly different subquery structures and focus on whether the queries truly do the same thing.
That sounds way more robust, a much deeper comparison. So what's the actual impact? How much better is ETM at evaluating these models?
The impact is pretty huge. Studies have shown ETM slashes those error rates we talked about. False positive rates from EXE, down from maybe 23%, and false negative rates from ESM, down from nearly 29%, can both drop to incredibly low levels with ETM like 0.3% and 2.7% respectively.
Wow, that's a massive improvement in accuracy.
It really is. ETM correctly handles all those tricky things. ESM struggled with joins, limits, different keywords, aliases, distinct in-lists, complex nested structures, parentheses ordering, the works.
Beyond just being more accurate, does ETM tell us anything new or surprising about how different types of text-to-SQL models perform?
It does offer some really interesting insights, yeah. For example, models based on general-purpose pre-trained language models, PLMs, which tend to generate SQL in more varied styles and sometimes make assumptions about the database, often see their scores go up significantly when measured by ETM compared to ESM.
Why is that?
Because ETM correctly recognizes many of their semantically valid but syntactically diverse queries that ESM wrongly penalized. On the flip side, models that are heavily fine-tuned language models, FLMs, often trained on very specific query patterns, might see their scores slightly decrease with ETM. This is because ETM is more stringent than EXE. It catches cases where the FLM's query only worked due to the specific data state, a false positive for EXE, but wasn't logically robust. ETM demands queries that work correctly always. Another interesting point. ETM tends to show a smaller gap between the best performing and worst performing models compared to EXE and ESM. This suggests it's a less biased, more reliable metric overall. It gives a truer picture.
Fascinating. So, better building blocks and now much better ways to measure. Let's pivot to the real world then. The data sets used to train and test these models have also been getting more complex over time, right? Moving beyond simple stuff.
Oh, absolutely. The field has really progressed. It started with relatively simple single-domain datasets. Then came cross-domain datasets like WikiSQL and the big one, Spider, testing generalization across different database types. After that, we saw multi-turn conversational datasets like CoSQL, where the AI needs to remember the context of the chat. Then came datasets specifically designed to test robustness, like SpiderSyn, which slightly changes the questions to see if the models break. And now, the cutting edge involves datasets that incorporate messy, real-world domain knowledge like KaggleDB-QA and SpiderDK. These reflect practical challenges much more closely.
Okay, so how complex are we talking now? When we look at multi-table question answering in the wild, what's the really hard problem people are tackling?
The real frontier now is tackling multi-table QA on seriously complex, often noisy, real-world datasets. A prime example is CISS, the Crash Investigation Sampling System database. These databases are beasts. Tables can have, like, over 200 columns.
200 columns in one table. Wow.
Yeah, and answering a question often requires multi-hop reasoning. That means you need to link information across multiple tables, sometimes 3, 4, or even more steps to get the final answer. Just figuring out those implicit join paths, how these tables connect to answer the question, is a massive challenge for AI.
Yeah, I can imagine. How can an AI possibly figure out how Table A relates to Table C via Table B without explicit instructions, especially in such complex schemas? How are researchers tackling that?
Well, one really clever approach is the Schema Graph-Assisted Multi-Table QA framework, or SGAM. SGAM uses a novel graph-based method, but here's the key difference. It leverages human-curated relational knowledge. It explicitly encodes those schema links and potential join paths into a graph structure before the LLM even sees the question.
Human-curated. So wait,
Yeah.
instead of making the LLM guess or infer how these super complex tables connect, SGAM basically gives the LLM a pre-built, accurate map of the relationships.
That's exactly the idea. SGAM builds a graph where database attributes, columns, are nodes, and the edges represent known relationships, primary keys, foreign keys, maybe other known semantic dependencies, even how some values are derived. This avoids relying on the LLM to perform that tricky, often unreliable, implicit schema alignment during the query generation process. It makes the whole thing more transparent, more controllable, more robust, and importantly, it makes the system more adaptable to new database domains without needing tons of retraining. It's kind of like a plug-and-play module for understanding the schema structure.
That sounds incredibly useful, a structural guide for the LLM. Does this actually work well on these really gnarly data sets like CISS?
The results are very promising. SGAM shows strong execution accuracy on these tough multi-table tasks, even with data as complex as CISS. And one really crucial finding that came out of this work is the importance of question decomposition.
Breaking the question down.
Exactly. Breaking a complex question into its core conditions and the main question part. This seems to be vital for multi-hop reasoning. For example, using GPT-4o on 3-hop questions in the CISS dataset. Its accuracy jumped dramatically when they added a question decomposition module first. It went from around 62% accuracy to nearly 92%.
Wow, that's a huge difference just from breaking the question down first.
Yeah, it seems to really help the LLM structure the complex multi-step SQL query much more effectively.
Okay, that's impressive.
Mhm.
But it can't be perfect, right? Even with SCAM providing the map, what are the remaining limitations or challenges?
No, it's definitely not perfect yet. SGAM still relies heavily on getting the initial attribute retrieval right. If the system doesn't identify the most relevant columns related to the user's question at the very beginning, the graph reasoning might miss vital connections later on.
Garbage in, garbage out, potentially.
A bit, yeah. Also, even with the correct structural connections provided by the graph, models can still sometimes make factual errors if they lack deep, specific domain knowledge, especially without fine-tuning for that particular domain. The graph tells them how tables connect, but not necessarily the subtle meanings or rules within that specific field. It's still an active area of research.
Right. Okay, so stepping back then, we've covered a lot of ground here. We've journeyed through this complex world of text-to-SQL, from its incredible promise-making databases easy for anyone to use, through the really intricate multi-stage pipelines needed to build these intelligent systems, and landing on the crucial and often underestimated challenge of actually measuring if they work correctly.
Absolutely. That journey from just typing a question in plain English to getting a precise, correct SQL query is definitely filled with subtle complexities. But as we've seen, real progress is being made. Advancements like the enhanced tree matching metric ETM give us a much truer way to evaluate these systems. And frameworks like schema graph-assisted multi-table QA SGAM are helping models tackle the kind of real-world data complexity we actually encounter. These things are genuinely pushing the boundaries, allowing LLMs to understand our questions and generate database queries with really unprecedented accuracy and reliability, even in very complex situations.
So thinking about the future then, what does this all mean for you listening right now? Imagine a world where getting insights from complex data feels,
Yeah.
well, totally natural. As easy as just asking a question, like asking a trusted expert. Knowing the answer you get back isn't just fast, but it's definitively correct. That future of how we interact with data is being built right now, one remarkably precise SQL query at a time.